Okay, hello everyone. Welcome to this week's Topos Institute Colloquium. This week we have Jonathan Gorard talking, but he has some co-authors in the chat. So for example, there's Mano in the chat, and Xerxes has just arrived. I will also make him co-host. So if you have any questions during the talk, I mean, there will be time for questions afterwards. Like spoken questions, but if you have any questions that you just want to put in the chat during the talk, hopefully either Mano or Xerxes can respond to these or interrupt Jonathan or something. Sorry, my internet went a bit bad there. So Jonathan, if you'd like to start, share your slides, and whenever you're ready, take it away.
Okay, well, let's see if this works. Okay, so thanks very much, Tim, for that very, very kind introduction. And thanks to both David and Tim for the extremely kind introduction to come and speak here at the Topos Institute. It's a great honor to be with all of you in Berkeley. Although I must confess, I'm still not completely certain what the Topos Institute is, at the very least, you guys seem to have some extremely interesting colloquia. So that's good enough for me. So today I'm going to be talking about some new ideas that are kind of emerging at the interface between mathematics, physics, and computation, and focusing specifically on some of the compositional aspects of those ideas and implications that they have for things like automated theorem proving, diagrammatic reasoning, and potentially, if we have time towards the end, to things like homotopy type theory, although that work is a little bit less developed. Okay, before I actually start the talk, let me just reiterate what Tim already mentioned. So a lot of the work I'm going to be presenting here today, at least in the first half of the talk, is joint work with Manognya Namaduri and Xerxes Asawala. So well, Mano, do you want to quickly unmute yourself and say hi?
Hi everyone.
And Xerxes, do you want to unmute yourself and say hi?
Hi everyone.
Okay, so yeah, as Tim said, if any of you have any questions that come up during the talk, obviously feel free to put them in the chat. And if you're having difficulty engaging with what I'm saying, either because it's really boring and you know it all already, or it's really confusing and you have no idea what I'm talking about, then please do engage with one of Mano or Xerxes instead. But okay, anyway, what am I actually talking about? So what's the big picture idea? The big picture idea is we know, and indeed we have known for some time, that there exists a class of problems in the foundations of physics that can profitably be reformulated as questions about diagrammatic reasoning systems over combinatorial structures. So be they string diagrams, typed graphs, hypergraphs, Petri nets, whatever. So one example that everyone here is probably familiar with, I know Bob Koech gave a talk on QNLP not too long ago here at Topos, is the ZX calculus. So the idea here is to represent any arbitrary linear transformation between qubits in some finite dimensional Hilbert space as a string diagram corresponding to a tensor network, in such a way that the rules for, say, finite dimensional stabilizer quantum mechanics can be formulated purely as graph rewriting rules over these ZX diagrams. So here's a partial enumeration of all possible rules of the ZX calculus. And so effectively, that allows us to reformulate questions about finite dimensional quantum mechanics in terms of questions about the rewriting structure of ZX calculus. So for instance, here's an example of what happens if we take a particular ZX diagram representing some quantum circuit and we apply all possible transformations in the ZX calculus. So we can address questions like, what classes of unitary transformations does quantum mechanics allow, or when are two quantum circuits of a particular type, when are they actually semantically equivalent, etc. All of those can be recast as diagrammatic reasoning questions. An example that you may be less familiar with, because this is somewhat more recent work, is the application of the same ideas but in general relativity. So for instance, if one is solving the Cauchy problem in GR, then one starts from a space-time, some Lorentzian manifold. One defines the Cauchy initial data on some space-like hypersurface, some Riemannian manifold. And that Riemannian manifold, we can approximate its geometrical structure as an undirected graph by, say, taking a simplicial decomposition or something like that. And then the problem of constructing the maximal Cauchy development of that hypersurface can be reformulated as a graph rewriting system over that undirected graph. Specifically, we can construct graph rewriting rules that provably obey the Einstein field equations in some appropriate limit, in such a way that we just apply the rules to that, to that hypergraph, to the graph or to the hypergraph, and we can evolve the system sort of arbitrarily far forwards or arbitrarily far back in time. So here's an example of Cauchy initial data represented as an undirected graph for a pair of black holes. And if we then evolve some graph rewriting system that obeys the Einstein field equations, these black holes merge, and eventually after some ring down phase, they turn into a single black hole. So this is being done purely on the basis of the graph structure. Even the colors you see here that are representing essentially the conformal curvature of space around a particular point in this hypersurface, that conformal curvature is itself extracted just from the graph information. So effective. Okay, I won't go into too much detail, but the basic idea is you can look at an individual vertex and you can construct a neighborhood graph consisting of all paths of length r emanating from that vertex. And by looking at the growth rate of that neighborhood graph, its highest order growth term will be r to the power of the dimension of the manifold, but the subleading terms give you information about the curvature. So the second order term tells you information about the Ricci scalar, and by doing a more elaborate version of that construction, you can using geodesic tubes and geodesic cones and things, you can extract information about the full Riemann tensor. And so we're coloring the graph vertices based on the conformal curvature, and actually from that conformal curvature, because we know analytically what the conformal curvature of the Schwarzschild solution looks like, we can even reconstruct what that space-like hypersurface should look like when the vertices are assigned coordinates. So here we're setting up a coordinate system for those vertices based on that conformal curvature information, and again using that effectively to simulate a binary black hole merger. So I'm not going to talk today about any of the kind of detailed physics of any of this. The key idea that I'm trying to convey here is that there exist large classes of questions in the foundations of quantum mechanics, in quantum information theory, in general relativity, and we also suspect, although we don't yet know, in areas like quantum field theory and even quantum gravity, that may profitably be reformulated as questions about diagrammatic reasoning systems for combinatorial structures. And therefore, the argument would go, if we want to better understand the foundations of physics, it is helpful for us first to better understand the compositional properties of such reasoning systems. And that's really what I'm going to talk about today. I want to talk about diagrammatic reasoning systems, their compositional structure, and how some ideas that come from the physics side of this formalism can help us to better inform, help inform how to better think about the compositional aspects of such systems. Okay, so let me actually get started with some content. So I'm going to start actually from a fairly traditional, fairly familiar origin point. So I apologize for the slightly elementary nature of my first few slides. I know many of you will already be familiar with a lot of these ideas. So the basic setup is we have some category G that just consists of two objects and basically representing the edges of some graph, and E and the vertices of some graph V. And we have a pair of, if we want to represent, say, directed graphs, we just have a pair of morphisms between E and V, one S corresponding to the source vertex of each edge, and one T corresponding to the target vertex of each edge, in such a way that any directed multigraph can be represented as a functor from G to set, and therefore the functor category G set gives us the category of all such directed multigraphs. And the reason we set things up this way is because although at first sight, this seems to be a setup for directed multigraphs. Actually, it's a very, very general way of thinking about combinatorial structures. Because, for instance, if we wanted to represent undirected multigraphs, then all we have to do is define a forgetful functor that just loses the information about which morphism is S and which morphism was T. Or if we wanted to represent arbitrary arity hypergraphs, as we will come to later on in the talk, then in effect, if one wants to represent hypergraphs with hyperedges of arity n, all one has to do is have n morphisms rather than just two morphisms. So all of this, just by changing effectively the Hom set, this basic way of thinking about combinatorial structures scales pretty well. So for the sake of concreteness, I will pretend that we're talking just about directed multigraphs, but it's important to know that this way of thinking actually is much more general than that. Okay, so then a directed graph or an ordered hypergraph can then for the sake of concreteness, we can then just think about that as being a sort of a set either of sets in the unordered case or a set of tuples in the ordered case, as we see here. Okay, so then in terms of how we sort of define a rewriting semantics on that, there's obviously a fairly standard way to do that in graph transformation algebras, and that's to use double push-out rewriting, to use DPO. And again, I'm sure this is something many of you are familiar with, so I'll go through this quite quickly. The basic idea is we have some span of monomorphisms rho that has a common domain K representing what's called the interface graph or the invariant subgraph, and codomains L and R representing the left-hand side of the rule and the right-hand side of the rule, so that any match is just a morphism from the left-hand side of the rule onto a given graph, and we can apply, and that match is applied by constructing a pair of push-out squares, or actually more exactly a push-out complement and a push-out square, where the intuition is the push-out complement square is responsible for taking the graph G, or taking a subgraph that's isomorphic to the interface graph K, and extracting out the left-hand side L, leaving just the interface graph. And then the corresponding push-out square is responsible for taking the right-hand side R and then injecting in back into the invariant subgraph K. And so, although DPO was originally constructed by, I think, Ehrig and others in the context of this category graph of directed multigraphs, actually it was later realized by Steve Lack and Pavel Sobocinski and others that this could be extended to by considering so-called adhesive categories. That is to say, categories in which this categories that are not the category graph, but for which this gluing transformation of the double push-out rewriting system still makes sense. And conventionally, these adhesive categories are defined in terms of these slightly opaque Van Kampen square conditions, which I won't talk about too much here. Those of you who know about DPO will know about this. Yeah, so the basic idea is that in that particular cubical diagram, there are sub-diagrams that are forced to be pullbacks. And then adhesivity is the condition that your category has push-outs along those monomorphisms, where it has push-outs along the monomorphisms. It has pullback squares of this form. It has the Van Kampen cube has faces of this form, and in which every push-out along a monomorphism is a Van Kampen square. But the particular point that I want to make for our purposes here is that the categories, because as I say, we're operating in this very general context where we want to be able to incorporate, ZX diagrams, string diagrams, hypergraphs, Petri net, etc. We actually consider not adhesive categories, but a more general class of objects called partial adhesive categories. And I don't know if these were developed solely by Kissinger or if they've just been very heavily promoted by Alex Kissinger, but certainly Kissinger has written a lot about these partial adhesive categories. So I won't say too much about them here, but the basic idea is there is a problem that exists with adhesivity, which is that if you take a product category or a functor category or a slice or a co-slice or something, then of an adhesive category, then the resulting category will itself be adhesive. But if you take a full subcategory with some arbitrary embedding functor, it will not in general inherit adhesivity. Nevertheless, the realization behind partial adhesive categories is that you can have you can take a full subcategory that still inherits sufficient adhesivity for one to be able to define DPO. And the basic idea there is really, really simple. You just say, we enforce the condition that the embedding functor from the subcategory onto the full category preserves all of the monomorphisms. And then what we can do is we can just import over all of the standard formalism of DPO, enforcing the constraint that the push-out diagrams and the pullbacks, etc., are all preserved by the embedding functor. So if the push-out diagram for this particular span of monomorphisms, in other words, the push-out along these monomorphisms exists and is preserved by the embedding functor, then this is known as an S span, where S is the embedding functor, etc. So we can define, correspondingly S push-outs, S push-out complements, and therefore S rule matches, which is just the same as the rule match condition for the ordinary DPO rewriting system, except under the constraint that both the push-out complement square and the push-out square have to be preserved by the embedding functor. Okay, and so that's what the particular setup looks like. Okay, so all of this is pretty standard stuff, so I'm not going to spend too much time dwelling on that. But okay, so here's a particular example of a rewriting rule on directed graphs, or if we want to think about these as being sort of as part of a more general context, we can think about them as being directed hypergraph or ordered hypergraphs of arity 2. So here's a particular sequence of hypergraphs that one would obtain, or directed graphs that one would obtain by applying this particular rule to an initial graph consisting of two self loops. And if we wanted to, we could drill down in more detail and see the structure of the individual rewrites being applied. So in this case here, the dashed lines are showing you where a particular collection of edges is being is being matched. That's giving you the left-hand side of the rule L, and everything that's left over is effectively giving you the information about the interface graph K, and then the red vertices, the red edges are showing you where you're then gluing in the right-hand side of the rule. And so here we're performing what we would call a generational evolution, where we're applying the rule to every non-overlapping matching subhypergraph. So you can see at the first step, the rule gets applied in one place. At the second step, it gets applied in two places. Third step, it gets applied in three. Fourth step in five, and so on. We build up a sequence of hypergraph transformations in this way. Okay, but first obvious point is that this notion that there's a unique sequence of transformations that one can apply is obviously wrong, right? In general, there'll be many possible sequences of transformations, and in general, they will yield non-isomorphic sequences of graphs or hypergraphs. So what one has is not just a straightforward evolution path. What one has is actually an abstract rewriting system. So, in the conventional context, you would think in the context of set theory, you would just think about that as being some set of objects, which in our case would be, say, hypergraphs, and a binary rewrite relation, which I'll denote arrow R. And in the more general setting, because we want to be able to represent things like ZX calculus, where in fact there are many possible rewrite rules, our rewrite relation is actually an indexed union of subrelations with some index set lambda. And so what we have is not just a state transition system. It's a state transition system that's labeled by the index set lambda. So it's a bijective map on lambda cross the object set. But if we wanted to think about that in more compositional terms, we could think about it as being, well, we can exploit the fact that the power set construction is just a covariant endofunctor on set, and therefore we can think about this abstract rewriting system as just being an F coalgebra on set. So we're just taking some object and we're introducing a morphism of set that maps from the objects, that maps from the class of objects A to the power set of that. Okay, so then if we wanted to visualize this abstract rewriting system or this F coalgebra in a slightly more concrete way, we could construct one of these things, which we call a multi-way evolution graph. And the idea behind this is really very simple. It's, each vertex is now an object in our abstract rewriting system, and each each of the gray edges you see, the directed gray edges, is a rewrite event. In other words, it's an application of this binary rewrite relation. So in other words, each vertex is representing a particular hypergraph state, and this overall directed acyclic graph, this multi-way evolution graph, is parameterizing all possible rewriting orders in which the vertices are being merged on the basis of hypergraph isomorphism. And then any given rewriting order or any given rewriting sequence is just representable as a path through this digraph. And so, for instance, the particular canonical rewriting sequence I showed you on the previous slide corresponds to this highlighted path here. Okay, but this is all fairly straightforward and fairly familiar to anyone who's kind of done things related to graph transformation or DPO, etc., or even is familiar with kind of term rewriting systems in general. So what is it that kind of what is it that we get by thinking about these about these systems in more physical terms that we wouldn't get just by thinking about them in abstract terms? Well, one thing that we realized was that if you take one of these multi-way evolution graphs and you squint at it for a bit, you realize that there's actually a bit more algebraic structure to it than initially meets the eye, that they're not just F coalgebras. There's actually a bit more going on. So in particular, what they are in the first instance is monoidal categories for a fairly simple reason, which is that if we look at one of these multi-way evolution graphs, clearly we can compose rewrites in sequence. That's how we obtain an individual rewriting path. But we can also compose rewrites in parallel. And that's corresponding to the fact that there isn't just one unique rewrite sequence. There's actually a sort of a parallel composition of a whole collection of rewrite sequences, a parallel composition of paths. And it's fairly natural to think about that, therefore, in terms of a monoidal structure. So with each evolution edge being interpreted as a morphism. And with a bit of effort, and as we did in the first, as Mano Xerxes and I did in the first paper that we wrote about this, we showed that this is indeed a monoidal category, satisfies the requisite coherence conditions, etc. But actually, there's a bit more going on than just being, being monoidal is not particularly special, but there's a few other interesting things that are happening here. Another is that actually these multi-way evolution graphs are equipped with a very natural involution operation, an involutive functor, which we can call dagger. Mapping from the opposite category onto the multi-way evolution category itself. And the reason for that is very simple. It's that given the span of monomorphisms that we have that's representing our rewriting system, we can just as equally swap the objects L and R. And if we're sufficiently careful about how we do that and we modify the interface graph in an appropriate way, that will have the effect of essentially inverting all of the directed edges that exist in this graph, in this diagram. So what we have is a very natural map from this multi-way evolution graph to its dual, or equivalently from the dual to itself. So it naturally comes equipped with a dagger structure that is moreover compatible with the monoidal structure, that is to say the composition, the ordinary composition or parallel composition of paths. But there's actually a third thing going on here. So these two properties, the property of the fact that these multi-way evolution graphs are really dagger monoidal categories. In fact, they're dagger symmetric monoidal categories. The reason for that is that there's a way you can formalize the monoidal structure in terms of a disjoint union of these indexed subrelations. And so then the monoidal structure inherits basically the algebraic properties of the disjoint union, including in particular commutativity. So we get a dagger symmetric monoidal category. But that would be true even if we were dealing with an arbitrary rewriting system, even if we were dealing with a boring, term rewriting system or something. There's nothing about that that's specific to the case of graphs or hypergraphs. But there's a third property that is, and that's the fact that this category is also compact closed. So specifically, given any hypergraph that exists in our multi-way evolution graph, we can take its dual. In other words, we can basically just swap the vertex set and the hyperedge set. So the new vertex set becomes the old set of hyperedges, and the new hyperedge set becomes the old set of vertices that were incident on that hyperedge. And so that gives us a natural involution operation on the hypergraphs themselves, and we can formalize that in terms of a compact structure, in terms of a unit morphism and a co-unit morphism in the Hom set of the multi-way evolution graph category, in such a way that it's compatible with the monoidal structure, therefore with the parallel composition, the dagger structure, and therefore with the rule inversion. And so we obtain a dagger symmetric monoidal category that is also compact closed. Okay, that means that, okay, so these multi-way evolution graphs are not totally trivial from an algebraic or compositional standpoint, but why does any of this matter from the point of view of thinking about the foundations of physics? Well, the significance, of course, is that therefore, as a dagger symmetric monoidal compact closed category, these multi-way evolution graphs have the same basic compositional properties as FdHilb. And moreover, in the more general context, have the same compositional properties required of any category in the context of categorical quantum mechanics, as developed by Samson Abramsky and Bob Koch. So, in other words, there exists a faithful functor from these multi-way evolution graphs to FdHilb, and therefore, at least in the kind of categorical sense, these are quantum mechanical objects. And that's kind of an interesting thing, because when one is first presented with with the fact that there is no canonical rewriting order on these hypergraphs, and therefore one has a multi-way evolution graph structure, if one tries to think about what that might mean from a physical point of view, one very tempting conclusion is you're basically saying, okay, well, at any given moment of time, there isn't a unique space-like hypersurface. There isn't a unique Cauchy surface. There's some kind of sum of or average of Cauchy surfaces at a particular level of the multi-way evolution graph, which again, it's quite tempting to think about that in terms of being a quantum superposition or something. And the fact that there therefore exists this faithful functor to FdHilb, and that we can now apply sort of the results of categorical quantum mechanics to these structures, means that actually we can start to make a bunch of those physical intuitions precise, and start to reason about these multi-way systems as being inherently quantum mechanical structures. So anyway, like I said, I'm not going to talk too much about the physics, but that's a kind of interesting connection there. And so because of this connection to CQM, we can start to make relationships to kind of other things that people have done in a similar vein, i.e. in terms of applying diagrammatic reasoning or combinatorial reasoning techniques to the foundations of quantum mechanics. So the famous example that I mentioned at the start is Bob Koch and Ross Duncan's work on the ZX calculus. So here's an example of exactly how we can actually see that monoidal category structure in practice. So if we take a pair of if we take some ZX diagrams like this and we just apply sort of two different collections of replacement rules to them. In other words, if we take our indexed union of subrelations and we just apply one particular subrelation to each of the two diagrams, then we get these multi-way evolution graphs here. But now if we applied both of these rewrite relations, both of the indexed rewrite relations in parallel, then we would attain this slightly more bushy looking multi-way evolution graph. And as I say, in the context of the multi-way system, this is interpreted as the monoidal product of those of the original two subrelations. And we can test that actually that's compatible with the monoidal product of the ZX diagrams themselves. So in the ZX calculus, the way you would take a monoidal product is just by stacking the two string diagrams on top of each other. So that's what we've done here with by stacking these two ZX diagrams on top of each other, and we obtain this multi-way evolution graph, and we readily find that it is indeed isomorphic to the up to state equivalence. It's isomorphic to the multi-way evolution graph that is obtained by just by taking the disjoint union of the indexed subrelations. And if we start to look at the so-called branch, so we could examine this in a bit more detail. We can look at what we call the branchial graph structure. This is essentially telling us exactly which collections of objects in the multi-way evolution graph are being composed monoidally. And the way that we work that out is we just look at the common ancestry distance in the multi-way evolution graph, and we use that to connect up these individual ZX diagrams. So in other words, if a pair of ZX diagrams forms a critical pair with respect to the underlying rewriting system, then they're connected by a single pink edge here. And if they form, if they have, so that would be the case where they have common ancestry distance 1. If they don't form a critical pair, but they still have common ancestry distance 2, then they would be connected. Then their path distance would be 2, etc. So we can actually see the monoidal structure of one of these multi-way evolution graphs explicitly by looking at these branchial graphs. And again, we can observe that if we take the monoidal product of the multi-way systems, we get a particular branchial graph structure. If we take the monoidal product of the ZX diagrams themselves, we get an isomorphic branchial graph structure up to state equivalence. And so I mean, as a first step, we tested this just empirically for a large class of rewriting systems and determined that it seemed to be a correct conjecture. And then we were able to use the fact that actually these open graphs, the category of open graphs is itself equipped with a monoidal structure. And we were able to show that this monoidal structure would indeed lift to the partial adhesive category of the rewrites. So this is a nice both theoretical and empirical validation that it is indeed a useful thing to do, to think about multi-way evolution graphs as being dagger compact closed categories. Okay, but in addition to the rewriting structure, there's actually a whole other sort of orthogonal thing that's going on with these multi-way systems, and that is we can start to look at not the rewriting structure of each individual transformation, but actually at the causal structure. So sometimes if you have a pair of rewrites, sometimes they're causally independent because they apply to different parts of the hypergraph, or there's no overlap between the inputs and the outputs. But sometimes they are causally related. Sometimes it's the case that you can only apply rewrite B if rewrite A had previously been applied. And the way we can formalize that in a sense is just by checking the set of hyperedges that were produced in the output of event A and the set of hyperedges that are sort of ingested in the input of event B, and checking whether there's a non-trivial intersection between those sets. And so we can construct what we call a causal graph, in which every vertex is now a rewrite and every directed edge is a causal relationship between those rewrites. So then what we get if we take the transitive reduction of that causal graph is the Hasse diagram for a poset, where that poset is essentially, the order relation on that poset is essentially causality. So it's an acyclic, well, actually, strictly speaking, it's not quite a poset, because by convention, it's not reflexive. I mean, we could easily make it reflexive by just adding self loops to each vertex, but we tend not to do that for aesthetic reasons. So it's almost a poset, but at the very least, it satisfies acyclicity / antisymmetry and transitivity, which is kind of all one cares about from the point of view of causal structure. So that's what these look like. So each on the left here, each one of these boxes is an individual rewrite occurring on a hypergraph, and each of the orange edges is a causal relationship between those rewrites. This on the right is the same system, just we've evolved it a little bit longer, so we start to get a more interesting causal graph structure. And okay, so one obvious question is, so how do we think about these causal graphs in a compositional way? Well, at some level, these causal graphs look a lot like the multi-way evolution graphs that we showed before. I mean, just in the same way, we can these causal relationships between events, we can compose those sequentially, so we get a sequence of causal relationships, or we can compose those in parallel. And effectively, if we want to think about that from a physics point of view, that's encoding the fact that if we're composing them in sequence, then that allows us to describe effectively time-like or causal separation of events. Whereas if we're composing them in parallel, that lets us describe space-like or acausal separation of events. And so this is encoding the fact that sometimes rewrites are causally related, sometimes they're not causally related. But crucially, unlike the multi-way evolution graph case, there's a key difference, which is that only some of these causal edges can be composed in parallel, because if the causal edges correspond to events, causal relationships between events that are time-like separated, that are causally dependent, then by definition they can't be composed but in parallel because they're not space-like separated. So what we get is not quite a monoidal category like we would in the multi-way evolution graph case. What we get is what we might call a partial monoidal category. So fortunately, the theory of partial monoidal categories has already been at least partially developed by Raymond Lowell and Bob Koch. So the idea, again, is fairly straightforward. We define a partial functor as just being a full functor from a full subcategory of the domain of the partial functor onto the codomain of the partial functor. And so then if the domain of the partial functor is a product category, then we call it a partial bifunctor. And so then a monoidal structure is just a partial bifunctor on C cross C to C. And we call the full subcategory of the this full functor f hat from the full subcategory of B onto C, we call A in that context the domain of definition, and we denote that DD. And so then Koch and Lowell laid down sort of the minimal sensible coherence conditions that would need to be satisfied by such a partial monoidal structure in their paper on relativistically interacting processes. So I won't go into that here, but the basic idea is that the associator, symmetry, left unit, right unit isomorphisms, when the sort of corresponding equations for those natural isomorphisms, those equations hold whenever it makes sense for them to hold. Where makes sense for them to hold just means that the left-hand side and the right-hand side of the equations both exist. That's the basic idea. Okay, so we're dealing specifically with symmetric partial monoidal categories. So they are equipped with a symmetry isomorphism. Again, in any situation where AB and BA are both elements of the domain of definition. Okay, so if we now enforce the condition that the associator, left uniter and right uniter isomorphisms are all identities, then of course we get a symmetric strict partial monoidal category. And so these therefore form, our causal graphs therefore form what in the terminology of Koch and Lowell are causal categories. That is to say, they are just partial symmetric strict monoidal categories that for which the designated unit object is terminal. Okay, but now we can actually, because there's the abstract rewriting structure and the causal structure are not separate, they're both part of the same rewriting system, we can somehow combine these two pictures together, the causal picture and the rewriting picture. So we can construct this slightly more complicated looking thing here, which we call a multi-way evolution causal graph. So in this context, each blue vertex corresponds to a particular state, a particular global hypergraph state. Each yellow box is a rewrite, is an event, and each orange edge is a causal relationship between those rewrites. And each gray edge is an evolution between, from one hypergraph to another. So it's showing both the rewriting structure and the causal structure in a single picture. Okay, so if we now try and think about that in a compositional way, this is quite an interesting kind of thing, right? What it's really telling us, very naturally, these multi-way evolution causal graphs seem to be some kind of weak two category. So what's happening is you have the one category which is coming from the multi-way system, in which each one morphism is a rewrite. And that, as I say, we know is a dagger compact closed symmetric monoidal category. But we also have those one morphisms themselves have two cells associated with them, because the rewrites themselves can be causally related, and so then the causal structure that you're imposing on top of that becomes essentially the two morphisms. And the interesting feature about that is that there are two monoidal structures that are kind of knocking about in this particular picture. There's the monoidal structure on the one morphisms that's coming from the multi-way system, and then there's the partial symmetric strict monoidal structure on the two morphisms that's coming from the causal graph. And so from a physical point of view, again, interpreting these hypergraphs as being, approximations to Riemannian manifolds or something, the monoidal structure on the one morphism is encoding the quantum mechanical side, and the monoidal structure on the partial monoidal structure on the two morphisms is encoding the relativistic side. And then this gives us a kind of nice kinematical interpretation of many of these isomorphisms. Say that the symmetry isomorphism of the partial symmetric strict monoidal structure then just becomes kind of a spatial inversion in the context of relativity and so on. And I should thank David at this point. So, okay, this is a pretty weird sort of compositional structure, and we weren't really sure of the right way to think about it. We're still not really sure of the right way to think about it. And so I wanted to thank David for one of our earlier conversations in which he proposed that both double categories and bicategories seem to be potentially fruitful ways of sort of formalizing what it is that we have in this particular picture. Bicategories in particular having the nice feature that, of course, the partiality of the causal monoidal structure emerges quite naturally when one thinks about it in the context of a bicategory. But as I say, we're still not really sure about the right, because none of us are really card-carrying category theorists. We're not really sure of the right way to think about this particular structure. And so if any of you guys have ideas or suggestions or comments about a sort of a clean and elegant way to think about exactly what it is that we're describing here, then that would, of course, be most welcome. And again, I won't talk too much about the physics side, but just as it's kind of interesting from a physical point of view, what this structure really is, because as I say, if we interpret the one morphism monoidal structure as being somehow quantum mechanical and the two morphism monoidal structure as being somehow relativistic, then the particular set of coherence conditions between these two monoidal structures, which we can derive actually directly from the multi-way evolution causal graph, those coherence conditions are effectively defining possible semantics for what I've put in inverted quotation marks are quantum gravity theories. So the reason I put them in quotation marks is it's not clear whether this is sort of quantum gravity in any physical sense, or whether it's just a kind of nice formal analogy to quantum gravity that exists in the context of graph rewriting systems. Of course, we would like it to be the former, but I think even if it's only the latter, it's already still a kind of interesting mathematical structure that's worthy of exploration in its own right. And so, okay, here's an example, a simplified example of what the causal semantics would look like, say, for the case of the ZX calculus. But actually, this is only showing the causal semantics for one particular indexed rewrite relation. If we showed it for all possible indexed rewrite relations, the full multi-way evolution causal graph structure looks much more complicated and hard to analyze. But still, there are the interesting thing is because there's this at least partial compositional picture that we can paint of this, there are still fairly generic, even though this is a very complicated kind of system, there are still fairly generic theorems that we can prove about what it does and what it means. Okay, so that's kind of a bit about the setup. What I really wanted to address next was what does this actually give us? What does thinking about graph rewriting systems in this slightly weird compositional way in terms of these dagger symmetric monoidal categories, what does that buy us that we couldn't get with just the standard algebra of graph rewriting? I should say, by the way, I mean, at least in part because I know Nick is in the audience, that a lot of the concepts that I've described here map very, very nicely onto the standard algebra of graph transformation. Like if you know about such things, the composition operation of the one morphisms in our multi-way evolution causal graph, that composition operation is effectively what the concurrency theorem in standard algebraic graph transformation gives you. And similarly, the parallelism theorem is essentially related to the monoidal structure. That is the symmetric full monoidal structure of the multi-way system itself. There's actually, it's a slightly different version of the parallelism theorem to the one that's conventionally presented in graph rewriting literature, because in the ordinary parallelism theorem, you are effectively your parallel composition of productions P1 plus P2 is assuming you have a sort of a sequence of a sequence of two rewrites, whereas in our case we're composing a pair of rewrites to get just a single rewrite, and so in a sense our rewrite relation is a bit different because it's essentially acting on it's not a rewrite relation from hypergraph to hypergraph. It's now a rewrite relation from hypergraph to critical pair or critical pair to hypergraph. So you get a slightly different algebraic object. And again, there's a lot of interesting mathematical work to be done in really understanding the algebraic structure of this and how how it sort of extends ideas that have already been addressed in standard algebraic theory of graph transformation. But anyway, that's a whole other talk. What I wanted to focus on now were some practical implications of thinking in these terms for doing things like graph transformation, for doing diagrammatic reasoning and automated theorem proving, and applying those techniques to areas like quantum information theory. So one really nice thing that we can do is, okay, if we wanted to define if we wanted to write an automated theorem proving algorithm for these diagrammatic structures, we might do that just using kind of fairly standard, critical pair analysis techniques, defining, an unveiling completion procedure, a Knuth-Bendix completion procedure on these on this class of diagrams, and that would work reasonably well. But in those kinds of, when one defines, say, a Knuth-Bendix completion procedure, the deductive inference rules that one is using always order the terms, or the graphs in our case, in terms of the reduction ordering. So if we treat our rewrite relation arrow subscript r as now being essentially a total order relation, then we can order all of the graphs and all of the subgraphs by that reduction ordering, and we can apply the inference rules, say, of resolution or superposition, etc., in accordance with that, with the, well, at any step, the deductive inference rule is always applied to the subgraph that is minimal with respect to the reduction ordering. But in fact, we now realize that's not the only way that you could do that, because another thing that you could do would be to order the graphs and subgraphs not based on the reduction ordering, but based on the causal ordering. So in other words, what we do is we pick, when choosing which inference rules in our automated theorem proving system we want to apply, we don't order them based on the reduction ordering. Instead, we order them based on the causal edge density. So the rewrites that get applied are the rewrites that apply to regions of the multi-way system that have higher than average causal connectivity. And the reason we do that is, oh, sorry, yeah, this is just repeating what I was saying earlier. So effectively what we're doing is we're defining a selection function that now, now the equations to which we're applying our deductive inference rules are maximal with respect to that selection function rather than being maximal with respect to the reduction ordering. And that selection function is just selecting on the basis of causal edge density. So the idea is, if you have a choice between two lemmas to introduce to your abstract rewriting system, one of which has high causal edge density and one of which has low causal edge density, you pick the one with high causal edge density. And the reason you want to do that is because the reason for introducing lemmas to your automated reasoning system is to shorten the proofs of subsequent propositions. And it's a reasonable heuristic that if the particular lemma you're choosing has high causal connectivity to future events, to future rewrites, it will also have the maximal effect on the shortening of future proofs. So this gives us actually a fairly general way of using this, this weak two category structure, the fact that we have both the rewriting structure and the causal structure, as a general approach to kind of optimizing automated theorem proving systems and automated diagrammatic rewriting systems. Now, again, I'm not going to go into too much detail about the specifics, but suffice it to say, it's actually a little bit more complicated than this, because if we want to do reasoning over, say, ZX diagrams or more general kinds of string diagram rewriting systems, then actually very often they're not encodable in a first order diagrammatic logic, as I've kind of implied, but actually they form some kind of higher order diagrammatic logic, because, for instance, the ZX diagrams, their rewriting calculus has sort of infinite parametric schemas of rules, like the fusion rules. There isn't just one, there's actually one for every possible configuration of input and output arities of the spiders. But anyway, and to address that, we effectively have to define a weakly complete and sound morphism from higher order diagrammatic logics onto first order multi-sorted diagrammatic logics equipped with the notion of equality. And again, the full details of that are available in this paper that Mano, Xerxes, and I put out just a few weeks ago. Anyway, so let me show you exactly what I mean. That all of that was probably a little bit abstract. Let me give you a concrete example. So suppose we have one of these Wolfram model systems, so some hypergraph rewriting system, and we want to show that given a particular input hypergraph, it's possible to reach a particular output hypergraph along along a particular rewrite sequence. So this is essentially a pathfinding problem, but we want to be able to solve that without having to tree out the entire multi-way system. So we apply an automated theorem prover. So what we do is we construct we develop this automated theorem proving algorithm for hypergraph rewriting systems. And so here is a proof of that particular proposition that this is the initial condition, the double self loop, and this kind of bow tie graph configuration is the final result. And here's the complete formalized proof that one is indeed reachable from the other. And you can see here we've produced a bunch of intermediate lemmas. So these orange boxes are substitution lemmas. Those are effectively applications of paramodulation and the paramodulation inference rule, and the yellow sort of triangles are applications of the critical pair lemma sort of idea. Those are sort of applications of selective resolution or superposition. Okay, so and here's this is a slightly more complicated example. It's slightly more algorithmically demanding to prove theorems in this particular multi-way system, just because it's much more tree-like, it branches much more rapidly. And so you get a slightly more sophisticated proof graph, but again, it's possible to synthesize these very, very quickly. And the nice feature of that is that now, because we're operating in this very, very general compositional context, we can use this, for instance, to do automated theorem proving over ZX diagrams. So we can effectively do automated reasoning in quantum information theory using this general approach. So here's an example of a proof of correctness of a simple quantum teleportation protocol. So this is the five generators on the left here are encoding Alice, some agent Alice sort of encoding a measurement in the Bell basis, and then on the two generators on the right are encoding Bob, sort of performing a sequence of measurements that are themselves classically correlated with Alice's. And what we want to prove is that reduces essentially to just a single communication channel between Alice and Bob. That corresponds to a proof of correctness of quantum teleportation in this particular formulation. And indeed, we can do that. So we can formulate a completely sort of automated derivation of that particular rule of quantum mechanics just from the first principles axioms of the ZX calculus. And the bit where that gets exciting is we can actually, because we have the information about the causal structure that most automated theorem proving systems don't have, and so because we're able to optimize our lemma selection strategies using that causal information, we can synthesize these theorems much more efficiently, and the proof graphs we get out are much better optimized than the proof graphs that would be got out if we didn't have that causal structure information. And so we can use this to do very, very practical things like simplification of circuits in quantum computing. So if we take some arbitrary quantum circuit specifying some quantum algorithm, then we can, there's a standard procedure that lets us reduce that into a ZX diagram, and then we can do automated diagrammatic reasoning over the ZX diagrams, find a ZX diagram that maximizes some simplification function. So, in our case, we were simplifying either to a pseudo-normal form, that is a graph state with local Clifford gates, or by reducing what's called T-count, by reducing the overall number of T-phase gates that are involved in the specification of the diagram. We did this with quantum circuits that were kind of randomly generated up to 3,000 gates, and we compared both the time complexity and the proof complexity with and without this optimization procedure, i.e. with and without using the causal structure information. And we found, as you can see from these diagrams, so this is on the left is without the causal structure information, on the right is with the causal structure information. You can see that there's actually, in this particular case, a roughly factor of 2, or a bit more than a factor of 2 increase in efficiency. And in the proof complexity, it's really, really substantial. So on the left at the top end, without the causal structure optimization, you can see that the proof graphs we were getting involved something on the order of 4 million proof steps at the top end, whereas with the causal structure information, it barely goes above 60,000. And this becomes even more profound for the more algorithmically challenging case of reducing the number of T-gates. And in general, what we found is that we get a roughly quadratic speed up, both in the time complexity and in the proof complexity, as a consequence of using the causal structure information, as a consequence of treating our rewriting system not just as an F coalgebra as you normally would in conventional rewriting theory, but actually as one of these two categories encoding causal structure information. Okay, this is more information about the proof complexity. So anyway, the basic point I want to convey here is that this isn't just a purely intellectual exercise. It does have some nice sort of semi-practical implication if you view quantum computing as being a practical implication. Okay, so just finally, I realize I'm about to run out of time, so I want to make a couple of just closing remarks about the generality and some possible future directions. So because we're in this very general context of a partial adhesive category, which subsumes these adhesive high level rewriting categories, these adhesive HLR categories as a subcase, specifically also subsuming categories like PT nets. This means that actually, although what I've been talking about has just been kind of fairly conventional DPO, we can encode things like Petri nets and their various extensions within the same framework. So here's an example of a multi-way evolution graph for a particular for a particular Petri net. That was after a single step. Here's the rewriting structure you get after 2 steps. And one interesting thing would be to look at how the compositional structure of the multi-way evolution causal graph for Petri nets compares to the compositional structure of the multi-way evolution graphs for, say, ZX diagrams, and whether they're how deep the analogies between the monoidal structure of Petri nets and the monoidal structure of string diagrams, how deep they go. And there's some nice connections with kind of standard algebraic graph rewriting theory, because in effect a single push-out rewriting system you can think about as being a Petri net with an extended Petri net that has read arcs and reset arcs, and a double push-out rewriting system you can think about as being like a Petri net that has read arcs and inhibitor arcs. And so there's a sort of a nice potential unification between the categories of nets stuff that's been going on recently and some of the work that we've been doing on these kind of extended DPO rewriting systems. Okay, just to finish, or I guess almost to finish, let me just make a final remark about some future work, about some work that's currently unpublished, but that we're undertaking, about the relationship of these approaches to homotopy type theory. The basic idea here is that when we map between a path in one of our multi-way evolution graphs and a corresponding proof graph, as we did in the previous cases, both for hypergraphs and for ZX diagrams, so we get this proof graph. But this proof graph is itself a labeled directed graph, not unlike a ZX diagram, which leads to an obvious question. Could we define a diagrammatic reasoning language on these proof graphs? In other words, could we define a reasoning language not on combinatorial structures in the abstract, but actually on mathematical proofs as represented by combinatorial structures? And it turns out the answer is yes. So for instance, these substitution lemmas that I mentioned that are effectively applications of resolution inference rules, they interact in fairly predictable ways. So for instance, if you have a pair of substitution lemmas, then they can fuse to form a single substitution lemma, and so long as one adds together the dependencies. And the intuition behind that statement is that if you have a pair of lemmas, one taking you from A to B and another taking you from B to C, you can fuse those into a single lemma taking you from A to C. And similarly, if you have a lemma taking you from A to C, you can fission it into a pair of lemmas A to B, B to C. And this applies to substitution lemmas with arbitrary arities, with arbitrary numbers of dependencies. And there are similar sort of diagrammatic reasoning rules you can define for the critical pair lemmas as well. So one can, for instance, if you have a critical pair lemma that's adjacent to substitution lemmas, then we can merge those all together into a single critical pair lemma and add together the dependencies. And the reason we're able to do that is because if you have a critical pair, A comma B, and so A can be rewritten to yield C and B can be rewritten to yield D, then now you could merge those together and form just a single critical pair lemma of C comma D. And you could get rid of the substitution lemmas, or you could perform the same procedure in reverse. And so, in fact, in all, we worked out a few months ago that there's a collection of what turn out to be 16 diagrammatic rule schemas, like the rules for the ZX calculus, that form a complete, consistent, and sound reasoning language for mathematical proofs, for essentially reasoning over these abstract proof graphs. And that's kind of interesting because it means once we can reason over them, we can construct their associated multi-way systems. And that multi-way evolution, so here's a multi-way evolution graph showing effectively all possible equivalent proofs of a simple proof in group theory. And so this multi-way evolution graph permits a very nice interpretation as the homotopy type for the associated proposition in group theory. And the reason that's kind of interesting is because now this gives us a hierarchical construction, because what we can do is we can say, okay, I start from some rewriting system. I take a path in the associated multi-way system. I convert that path into a proof graph. Now I can construct a higher order multi-way system based on that proof graph, constructing all possible equivalent proofs. That is effectively the homotopy type. And then I can take a path through that and then construct its proof graph, and then I can build a multi-way system from that, and so on. And there's a whole infinite hierarchy of higher order multi-way systems that I can construct. And it turns out, again, that this gives one effectively a systematic way of constructing, by means of diagrammatic reasoning, arbitrary high-order inductive types. And so this gives one essentially a pictorial language for reasoning about mathematical proofs, and therefore for kind of thinking about homotopy type theory in general. But again, I also want to emphasize this is not just sort of intellectually interesting, it's also pragmatically important. So the initial reason why we actually started developing this was not primarily to better understand homotopy type theory. It was actually to build more efficient theorem provers. So if you have an automated theorem proving system over a diagrammatic reasoning system, and it outputs some proof graph, a path corresponding to some mathematical proof, there's no guarantee that that path is optimal. In fact, in almost all cases, it won't be, because the theorem proving algorithm is just going to output the first proof it finds. It's not going to bother to find all possible equivalent proofs and find the shortest one. But actually, once you've got a proof, and once you have a diagrammatic reasoning system on proofs themselves, then we can construct a multi-way system of all possible equivalent proofs, and then do effectively like the ZX diagram circuit optimization problem, but now it's sort of abstract proof optimization. And so we can have a level, if you like, a level 1 theorem prover that produces the initial proof. Then we have a level 2 theorem prover that's responsible for shortening that proof and proving equivalence between the original proof and the shortened proof. But then the proof of equivalence between those proofs is itself not optimal. So then we can have a level 3 theorem prover that optimizes that, and so on. And so actually this ability to go to higher inductive types in this purely diagrammatic and formalized way gives us a way of effectively using these higher order inductive theorem provers, if you like, in order to optimize the proof complexity, reduce the proof complexity of proofs generated by sort of conventional first order theorem provers. So anyway, there's a lot more work to be done on that. And if I may end with just a slightly cryptic and very speculative remark, just as sort of ZX calculus is is a way of thinking about quantum mechanics in the kind of, but at the level of one categories. And given that this sort of homotopy type theoretic construction gives us a way of essentially going to at least an infinity zero category, so at least some weak Grothendieck infinity groupoid, there is a conjecture that we have made that effectively this construction, the same functor that maps from ZX diagrams to FdHilb in the categorical quantum mechanics case, as we take this to kind of to the infinity category context, that functor will essentially give us a topological quantum field theory, in the sense that the monoidal structure will sort of lift to be some kind of cobordism relation between topological spaces in that weak infinity, Grothendieck infinity category, and then the functor from that category of cobordisms to the category of vector spaces will give us exactly a TQFT. But as I say, that's a slightly sort of outlandish speculation, and I think if it's even true, I think we're several steps away from being able to prove that. But I wanted to give some indication of where we think this sort of general program may be leading from a physics point of view, as well as just from a mathematical structure point of view. Okay, so I've probably spoken for too long. Let me end it there, and I can see there have been loads of questions in the chat, so maybe we can take some of those.
Brilliant. Thank you, Jonathan, for the talk. That was great. Yeah, there were some questions in the chat that have been answered, I think. I'm going to make it now so that people can unmute themselves. So if anyone has a question, feel free to unmute yourself and ask.
Oh boy.
Maybe I'll kick it off. Thanks, Jonathan. That was a great talk. Very cool stuff. I was wondering, are these diagrams that you showed, all these pictures, I think you indicated at some point that a lot of this stuff was available on GitHub or like freely available. Are the ways that you're doing this things that other people can use?
Yes. Okay. So I should have had that as my last slide. Thank you. Well, in fact, hang on, wait. I can. It is the last slide of a different talk I gave recently, so I can show that instead. But yes. So all of the visualizations I showed here, including all of the recent ZX calculus stuff, that's fully open source. It's available on our function repository. If I show that thing here, so you can see it. So if you go to wolframcloud.com/function repository and you just type in the name of any one of these functions, multi-way operator system, make ZX diagram, etc., then you can download a documented notebook and all of the source codes to reproduce all of those visualizations. And in fact, in a quite cool way, this is very recent. This was just released a few days ago. There is now more or less complete integration between the ZX calculus framework and our inbuilt Mathematica quantum computing framework, and also our multi-way system framework. So all these kind of not only can you use these functions, but they all interoperate with each other reasonably well. But yes, so all the code is open source if you want to use it.
Great. Well, thanks a lot. I might ask another question later, but I'll keep it open for other people.
Okay, so I think Paul had his hand up next. So Paul, do you want to ask your question?
Yeah. Okay. So I'm a one category to a very long time ago was interested in relativity. Can you tell me what piece of category theory, what categorical idea are you using to capture causality or the distinction between time-like and space-like separations of things?
Right. Okay, so that's the idea behind the partiality of this monoidal structure. So so from a compositional, from a pure poset standpoint, this is kind of trivial, right? If you think about these causal graphs as just being posets, then space-like separation just refers to the fact that you have a collection of events that form an anti-chain, and time-like or light-like separation is when they don't form an anti-chain, when they are related by the partial order. So when we translate that into the compositional context, that just becomes the distinction between whether the associated causal edges are related by this partial monoidal structure, which would mean that they are space-like separated, or they are not related by the partial monoidal structure. In other words, they are just related by ordinary sequential composition of morphisms, which would be the case when they are time-like or light-like separated. In practice, we don't, in the discrete context, we don't tend to make the distinction between time-like or light-like separation, although you can do, there's a way you can do it in terms of degeneracies, but it's overly complicated. Does that, maybe I misunderstood your question. Does that?
Yeah, well, I think you understood the question. I was hoping for some deeper piece of category theory that might be the explanation of it, thing like that. But if there is, fair enough.
No, if there is I'd love to know if there's a deeper piece of category theory that explains it. But I'm probably not the right person to ask, and I was hoping this audience would be.
Off the top of my head, I suppose there might be this distinction between ordinary composition and monoidal composition in so it might be you might take some ideas from separation logic or something like that, but that's merely off the top of my head. I'm not suggesting that's the answer to the question.
No, but that is what's going on. The distinction in separation logic is exactly of this kind, right? That some things are monoidally related and some things are just related by sequential composition. And in our case, the monoidal relationship is the space-like one, and the sequential relationship is the time-like one.
Okay.
Whether there's deeper analogies with that, I don't know. It'd be interesting to figure out.
Okay, I'll shut up.
Okay, thanks. So I think Lee had his hand up next. So Lee.
Okay. Can you hear me clearly?
Yeah.
Yeah, great. So I was wondering if you have thought about or interested in a kind of analogy to quantum field theory in the whole Evo-Devo community, trying to understand the kind of relationship between the local and the global, just quite simply. And we all know that evolution is based on the notion of gene mutation combined with trait selection. And I think of this in my wildly analogously oriented mind as somewhat analogous to the complementarity of the quantum and the relativistic, but I think it's more than fanciful because in the last 10 years there's been a lot of debate in the community about network thinking. Before we knew anything about genes, it was about what we now know about genes. There was just a notion that genes and traits are in one-to-one correspondence, and there was no real discussion. But since the 50s, there has been a focus on gene regulatory networks, the interaction as being the link between what I would call, the Evo-Devo analogy to quantum field theory, that if we focus on our network thinking, on gene regulatory networks, we can pull these two together. However, in the last 10 years, there's been a kind of like a pushback that network thinking isn't adequate, not fully explanatory. And then there's been pushback to the pushback in the recent years, saying, yes, we can. And listening to this talk, I'm wondering whether this sort of somewhat aggressive behavior, never do I kind of feel it's helpful in science, maybe can be resolved by looking in the direction of just what you spoke about today, because there isn't too much sophistication among biologists at the level of today's talk. When they think of networks, they don't talk about rewrite systems. This is not in there. So long story short, do you think there might be fruitfulness in bringing this perspective into this ongoing debate, which has been oscillating recently? Was my question clear?
Yeah, it was clear. I mean, long story short, yes. I mean, I'm not familiar with this particular analogy between evo-devo biology and QFT. That's an interesting one.
That's just my analogy.
Okay. That may be why I haven't heard of it. We should discuss that more. But yeah, if there's a way effectively to if there's a similar sense in which one can, I think I understand the nub of your question, which is if there's a kind of similar sense in which you can think about the distinction between the sort of phenotype, which is really the semantics of biology, and the genotype, which is really the syntax of biology, as being analogous to the causal structure, which is really the semantics of our model, versus the multi-way structure, which is really the syntax of our model. Yes. If there are similar algebraic or compositional ideas that apply to those two cases, that sounds very plausible. We'd need to talk to an actual biologist to find out. But yeah, that's a very, very interesting idea. Maybe we could talk about that offline. I don't know if Mano, or particularly Xerxes, who is a sort of physically, biologically informed physicist, whether you guys have ideas about that.
Not more actually at this point, but indeed some of the initial interest in this network thinking in biology was to hope that you would pick up global ideas or global invariants as opposed to looking at purely local information. Yes. But it seems from the way we are constructing our systems, our rewrite systems here, there is a notion that there might be more than just looking at networks of dyadic structures. And there might sometimes be global information at even higher levels. So in every field, whether you're looking at biology or looking at computation or you're looking at physics, the relevant question is at what level are the invariants that you're looking for? In some quantum field theories, you might simply work with one order morphisms. In some, you might go up to second order, and there you might find interesting invariants. I don't know what the answer would be for this genotype phenotype debate. Maybe there it's more complicated. But at least here, systematically, the way we are constructing these higher homotopies, we might be able to study quantum field theories at some levels, and hopefully for physics that might be a little bit more relevant in the way we understand it currently.
Mm-hmm. Thank you.
Actually, just since we're on that topic, I wanted to mention just one quick intermediate thing. So in terms of this bridging the gap between what we have right now, which is pretty solid description of categorical quantum mechanics, and this very, very wild speculative proposal I made at the end about topological quantum field theories, one intermediate case of that we're currently working on is essentially the case of spatially extended ZX calculus. So what happens if we take a ZX diagram, which has no kind of spatial structure to it a priori, and we embed it into, for instance, the background hypergraph of one of these Schwarzschild solutions that I showed towards the beginning, and we modify the ZX rewriting rules in such a way that they take into account the existence of the background spatial structure, so that there's effectively a finite speed of light and those kinds of things, then essentially the conjecture would be that sort of diagrammatic reasoning language, which is a much more attainable short-term goal, which we're working on right now, may offer some kind of intermediate case between bog standard CQM and kind of full TQFT, and hopefully we'll know the answer to that pretty soon, and then at least we'll have more sensible things to say about the QFT side, if not the biological analogy.
Thank you. Thank you.
Okay, thanks. So I think Andreas, you had your hand up next.
Yes. So I'd like to ask, way back near the beginning of the talk, you mentioned a compact closed structure that essentially amounted to interchanging vertices with hyperedges. And if you said it, it went by too fast. The incidence relation is to be preserved in this interchange, because it seems to me that I keep running into situations where you interchange two sets with some relation between them, but you also take the complement of the converse relation. This comes up in Valery da Paiva's dialectica categories. It comes up in Von Pratt's Chu spaces. It came up in some work that I did. It just keeps popping up all over the place, and I'm just wondering whether it may have some relevance in your situation.
That's very interesting. Okay, so I don't know this particular piece of work. It would be very interesting to chat afterwards about that. So just to answer your initial question, so in the particular the compact structure that we're dealing with, we're not exactly preserving the instance relation. We're taking the transpose of the instance matrix, which I get. I mean, so we're preserving it.
The converse as closely as you can while reversing the domain and the codomain.
Exactly. But it sounds like you're dealing with something that's a little bit more sophisticated than that in the context of these dialectic.
Essentially, complement of converse.
I see. Okay, that's interesting. I see. No, we haven't thought about that. That's an interesting suggestion. Yeah, it'd be nice to chat more about that.
Thank you.
Thanks.
Okay, wonderful. And David, then I guess you are allowed another question.
Okay. Yeah, I was also wondering about the hypergraph part. So I understood that the category we were talking about, or the Monoidal category, was in the context of some rewrite rules, some double push-out rewrite rules, and that the morphisms were the activation of one of those rules. Did you say, when you said it was compact closed, are you saying that like I must have it wrong, but it sounded like you were saying that automatically, no matter what my rules are, there's a cup and cap that eliminate a hypergraph and its dual.
Right, yes.
So if I had the empty set of rewrite rules, I couldn't eliminate the hypergraph and its dual, right?
Is that true? Yes. Okay. Hang on. Yes, that is true. Yeah. Okay. Your index set can't be empty.
But if I had a stupid rule, a stupid double push-out rewrite, how do I know that you will always be able to eliminate a hypergraph and its dual?
Right. Okay. So you're getting onto a subtlety here that's an important one. So our proof of the existence of this compact closed structure depends on the fact that it is possible to distinguish between local and global confluence in the rewriting system. And we know that that only happens in cases where the system is non-terminating. The reflective, if we take the reflective transitive closure of the rewrite relation, that reflective transitive closure is not well-founded, is a necessary condition for that particular argument to apply. So in the particular instances that I was talking about here, like ZX calculus, we know that that's true. But yeah, it wouldn't necessarily be true for any system in which that rewrite relation were well-founded.
Okay, so like for any hypergraph, there are some kind of systems of double push-out rewrite rules for which, if I have any hypergraph, its dual and it would form the left-hand side, would be left-hand sideable.
Right.
And you
exactly.
could just completely eliminate the entire pair and get your cup. Wow. Okay, that's surprising, but I'll have to take a look. Thanks.
Okay, and then we have Nicholas who's put the hand up. So,
thank you. So thanks again. I mean, it seems like watching this talk more often helps. So I mean, I just wanted to comment on one piece which seems to be interesting. I'm not quite sure. So I mean, you seem to have two directions you can either sequentially compose, which because I mean, you're building essentially graph states. An arrow between two graph states is a concrete rewrite. So it's not only picking a particular rule, but it's picking a particular occurrence of the input motive to then apply that rewrite. Yes. So I mean, we would call that a direct derivation in graph rewriting. Right. But then if you do two paths, there would be a sequence of two direct derivation. then something interesting happens, because you were very clear about this. But so the parallelism theorem in the writing says, if you overlap along an empty overlap, so you perform two rewrites, but there are instances where you rewrite do not overlap. In that case, you precisely emulate the parallel application. So I mean, what's strange to me a little bit, but maybe I misunderstood. So parallel application is emulated by sequences with trivial overlap. So that should mean something, because I mean, how do you determine your rule set? I think I'm following up on David's question a bit. So do you allow a particular finite rule set plus all of parallel applications? Or do you just start from a finite rule set and sort of build up only sequences? So I didn't get where you get the parallelism from.
So there's no effective rule for parallelism, if that's kind of the core of your question. That we're not introducing rules that deal with the parallel application case. The structure of the rewriting system itself deals with the parallel application case. What we're not doing, and we're also not enforcing the constraint that you're referring to, that effectively the rewriting system is orthogonal. So in our context, parallel rewrite means both overlapping and non-overlapping cases of parallelism.
So what do you mean by parallelism then, just to be sure?
Right. So this was the comment I was making earlier about, so ordinary parallelism theorem, you essentially, you're assuming you have two sequentially independent derivations, right? You have P1, P2.
Oh no, sorry, I forgot to say. And then the concurrency theorem tells you the composite rule of these sequential non-overlapping things is exactly what you call the parallel rule. So it's just so where basically the input motives are disjoint unions, and then sort of essentially a complete disjoint union of the spans, if you will. So that's
right. No, so I understand. So with concurrency, you're constructing an e-concurrent production from a pair of initial production
along to be overlap. Yeah.
Right. So the point I was making is that, in a sense, our way of thinking about parallelism is somehow the sort of like the square root of the ordinary parallelism theorem, because you're not treating a P1, P2, P2, P1 pair of sequentially independent derivations. What you're doing is and then composing them to get P1 plus P2, which is what you would do in the parallelism theorem, as I understand. What you're doing is you're actually directly composing P1 with P2, and you're defining a rewrite relation that is essentially mapping not from hypergraph to hypergraph, but from hypergraph to critical pair. And that's the relationship that's relevant to the monoidal structure.
And so other ways that you just have an operation of disjoint union, so to speak, of rules. So this way you create new rules. Actually, you create arbitrarily many new rules. But in your diagrams, you select by hand a finite set of rules. Might include parallel rules, might not. But I mean, so basically, you by hand distinguish between the two effects. That's what you're saying.
I see what you're saying. Okay, so okay, right. So you're making the relevant point. Okay, yeah. These disjoint unions you can think of as being effective, introduced effective rules. And yeah, okay, so then yes, and they implicitly form part of the abstract rewriting system. So
if I were a user and I would use the parallel rules as part of the finite input rule set, I would mix space and time-like separation then.
Exactly. Yes.
Okay.
Right. Actually, it's even worse than that. You would, depending on how extreme the overlap was, you might even mix space-like, time-like, and branch-like separation, which is the kind of the worst possible case.
Okay, thanks.
Okay, does anybody else have any questions? Seems like not. In which case, I'd like to thank you again, Jonathan, and thank you as well, Mano and Xerxes, for being in the chat. And thank you, yes, for a wonderful talk. So another small round of applause. And we will see everyone next week for the next talk. Thanks. And I'm going to stop the live stream, but I'll leave this room open if people want to hang around and chat in it. But there's no obligation to. So.